Go.
Good morning, ladies and gentlemen. Go ahead and take out your notebook if you don't have it out already. And we're going to go ahead and do a quick do now, a little like mini quiz. Just to see if you know what's going on. So what does each symbol represent and what are its units?
So 2 things for each one.
So what does it represent? What are the units? What do we call these things? What are their names?
Pause the video, do it, and we'll come back.
All right. You guys done? Yes, Miss Moore? Okay, so check your work here. So if you guys were in class, we would grade this, but I mean, we're not gonna grade it. Give yourself 1 point if you got each of these correct. E was for our electric field. Our Q prime is our test charge. W is work. And our delta V is electric potential difference.
It's a lot of syllables.
Yep. Do you guys get that?
Those are what they stand for, and then
Boom! Here are their charges. So for the electric field, it is a Newton Coulomb.
Newton per Coulomb.
Force over the test charge, right?
Yep.
And then test charge is a Coulomb, which makes sense. W is work, which is joules. And our electrical potential difference is volts.
Yep, those are the units of electrical potential difference.
Okay, so if we were grading this, it would be 1 point for everything, 8 points total, but, you know.
We ain't gonna do it. We ain't gonna do it.
Let's keep going. Okay, so here is our lovely equation. We know that the electrical potential difference is equal to the work over the test charge.
Work done moving charge around in an electric field.
So work over the test charge is our delta V. Okay. All right. Question. Okay, so you pump 0.8 coulombs of electrons from one plate to another in a capacitor. How much work did you do if the delta V
So you pump
is 8
electrons
volts?
from here to there. You had to crank that handle to do work. How much work did you do?
Oh, or even if you have, I just put the ball away. Another way you can think about it is, okay, you pump 0.8 coulomb charge or 0.8 coulomb charge electron from one plate to the.
Well, no, that's the test charge inside the field.
Oh, wrong.
It's a lot simpler than that. It's just solve that equation for work.
Okay, so let's do it. So let's see, what was our work up there?
0.8. Oh no, we don't know
We're
that.
solving for work, right? We're solving for work. So how do we get rid of how do we get rid of work?
Well, you don't get rid of you get rid of the Q prime.
I'm saying the wrong things, you guys. Hope you're like Miss Moore. That's wrong. Okay, so work equals. How do we get rid of the test charge? Work is the electrical potential difference times the test charge. We can do this, right?
Yeah.
Okay.
That's 8 volts is
8
the potential
volts.
difference.
Okay.
And
multiply
0.8 coulombs.
0.8 coulombs. Is that going to be 0.1?
No,
No.
what's 8 times
No,
8?
10. It's going to be 10.
What's 8 times 8?
6.4. It's going to 64, right? Oh no, I left my calculator at home too.
0.64.
0.64. Okay.
You got a bunch of other
Oh,
calculators.
you're right. They're in the back. Let me grab them real quick. So today's the first day that I'm back at school, and I left a few things at home.
They painted the walls.
Yeah,
Some of the
you know
walls.
what? They look nice, but take a look at my room.
It's a mess.
Kind of a disaster. Okay. 0.8 and Mr. Boyd. Oh, 6.4. 6.4.
Oh, did I say 6.4?
Oh, that's a nice calculator. 6.4 joules.
What is that, like teal and gold?
Yeah, and this is probably the first time this has ever been used. It's so crisp. Okay. All right, so moving on. Oops. We have our good old Ed. Electrical potential difference in a parallel plate capacitor is represented by Ed.
And that's the relationship between the intensity of the electric field, the distance the plates are apart, and the change of potential energy from one point to the other.
Okay, so if the plate of a capacitor is, not my equation, we say N.
Yeah.
Okay, so if the plate of my capacitors is 0.004 meters apart and the delta V is 8 volts, what is the intensity of the electric field? Okay, so I need to solve for this one then, right?
Yeah.
Okay.
That means the distance from here to here is 0.04.
0.004.
So D 0.04. And the intensity of the electric field on the inside is, oh, wait a minute, that we don't know that yet.
We're trying to find
So
that.
the potential difference would be
Delta V is what?
8 volts.
8 volts. Okay, so I'm just gonna go ahead and write this over here now because I'm over here. Okay, so we want to figure out what the intensity of the electrical field is. So
How do you get rid of D?
I'm gonna divide because right now I've got multiplication. Okay.
Boom.
All right, so delta V divided by D. Delta V is 8 volts divided by our distance is 0.004.
I think it's going to be 200. I'll bet it's 200. It's
200?
either 200 or 2,000.
So 8 divided by 0.004, and I get 2,000.
Ba-boom!
2,000, and our electric field is a Newton Coulomb.
Yep.
Okay. Feeling good, guys?
Yeah.
Get rid of this extra one right here. Okay. This little guy again. Okay, so a couple, was it yesterday that we had
Yep.
you guys, we put these words up here and we drew our diagram and we talked about, how could we explain what's going on within our capacitor using these words?
Yeah, and we did that with the electron pump of the capacitor, but it's also the same thing with the Wimshurst machine and the pi plate capacitor.
Mm-hmm. So I'm gonna go through this one more time with you guys. So we have a capacitor and it has 2 plates.
Yep.
Okay, and we turn our pump.
Go ahead, turn it.
Yeah, we oh,
Easy, girl.
okay,
You're doing work right now.
Yeah, we do work.
Whoa!
Whoa, did it work?
It did.
It totally worked.
Hear all that crackling and stuff? All right. So now, whoa!
Mr. Boy, it did it again.
Woo! All right, so you're doing work and you're pumping, their electrons are flowing, sweet, from one plate to the other. And what happens when you take an electron off of the positive side?
So when we take it off the positive side, it is going to have, it's going to be attracted to this side, but this side is going to have a greater force of repulsion.
Well, if you're taking electrons and you take it away from the positive side, it's going to go, no,
Yeah.
making protons.
Yeah.
It feels a force of attraction.
Yeah. So it's feeling that force of attraction with the top side that's positive, right?
Yeah, and then you pump it to the other side and try to put that electron where it's all negative.
And it's experiencing,
Get away from me! No, I ain't going in there.
right? Yeah. And the whole thing is we're putting in work, pumping these electrons from this side to this side.
Yep.
And these are experiencing repulsion, and these ones are they're attracted to that, right?
Yeah,
They
and
want to go back there.
And in between, there's an electric field.
Yes, and so because we create, because we pump these electrons over here. Now we have a difference in charges, right?
Yeah.
And we're creating that field, and that field it has an electrical potential difference.
So all that work you did was stored an electrical potential difference between the plates.
Yeah, just like our UG, right?
Yeah.
Gravitational potential energy, electrical potential difference here. Okay, so let's go ahead and
I think that's the end, isn't it?
we got one more slide.
Oh,
Okay. Electrical potential difference is measured. So what is this measured with? A voltmeter. Okay. It's time for our lab.
so
Okay.
this is we'll talk about the voltmeter first. Here's a voltmeter.
This is our voltmeter, and it measures electrical potential difference.
Yeah.
And it has V there because the units for electrical potential difference are volts.
Volts.
Yes, volts. Okay, so we have one black, what do you call this, like input?
It's a post.
Post, okay. And then we have 3 red ones. Why do we have 3? Well,
Sometimes you have little voltage, sometimes you got big voltage.
yeah, and so we have different scales here. We have, so this one is the 3 volt one, which is right there. This is the 15, and that represents the 300
So
volts.
depending on which pole you have the wire lead plugged into, you read off of a different scale.
And so we're plugged into 15, so we're going to be reading on this bottom scale.
All right.
All right, so
They have a copy of the.
yeah, you guys have a copy of this. It's on Canvas for you. So tell me again, what are the units of displacement, force, work, of the electric field, and potential difference?
So, in fact, they should do all of this before we start playing with
Yeah,
stuff.
you guys should do, do that first one. Tell me, what is a capacitor? And then tell me, what does a voltmeter measure? I just gave you the answer to that.
Don.
Okay. So now that you guys have done that, pause the video.
Pause the video.
First, okay. And let's go ahead and start reading what's going on here now. So it says materials. We've got our capacitor, we've got our voltmeter, and we have the leads right here, and we have our electron pump. Okay. Oh, and then our electron pump leads.
Yep.
Let's talk about this. Okay, so this is our pump. This just like with the Wim Hof, not the Wim Hof.
Wimshurst.
Sorry, Wim Hof. The Wim Hof method is a breathing method. The Wim Hurst machine. We have this crank. What is it?
Yeah, it's a crank, and
And
what
you
it
can-
does is it pumps things.
It pumps things.
Pumps
Okay.
electrons.
And we have two wires here. Can you guys see that?
And inside are metal conductors, so electrons are free to move inside
Yeah.
a conductor.
Yeah, they're free to move here, and we have a pink one and a silver one. And electrons are going to move
There.
in both of them
Yeah.
respectively. Okay. Okay, so step one. So voltmeter, connect the red lead from the red post marked 15 on the voltmeter to the positive post of the capacitor. Okay, so we put this in here. That was the beginning, and it wants us to put this onto the positive part of the capacitor. You see that plus sign there?
Plus sign.
Yep. Okay, so I'm gonna go ahead and connect it like that. Okay. Connect the black lead from the black post marked negative on the voltmeter to the other post of the capacitor. So this is gonna go right here where it says
Yeah.
negative, and then this one just goes over here, like that.
And Mr. Boykin tied this in a knot because this thing's about 3 feet long. It'll be spaghetti on the table.
Okay, so step one is done. Step two, electron pump. So bite the pink lead from the electron pump to the red lead on the positive post of the capacitor. Pink. And I'm just gonna go ahead and bite it right there. Okay. Let's see. Bite the silver lead from the electron pump to the black lead of the the capacitor. Meep. So here we go, right there. There's our silver one. Okay.
All right.
Now, before we go any further, think about how this is like that up there, that drawing.
Yeah, the electron pump has got the little S inside of it. And what it's doing is pumping electrons from one side to another when you turn the handle.
Oh, and interesting, you've got one blue thing going to the top and one blue thing going to the bottom. That's kind of like the pink and the silver,
Yes.
right?
Sure.
That makes sense? Okay. Okay, so now it says step 3, turn the handle on the electron pump clockwise several times, and then let go. Okay, describe everything you observe here. Okay, so let's do this. Ready? What'd you see?
Well, do that again.
Okay, here we go. Huh.
All right. Now,
Okay.
stop the video and answer the question.
Go ahead and describe everything that you observe here.
What did you just see? And if you need to run it back, go ahead.
Yeah. Okay, let's talk about what we saw.
No,
Let them do it?
that's their job.
All
and,
right.
and you can talk about it when you grade it.
Oh, okay. And then in terms of electrons, describe what caused all of this.
I mean, we've been talking about this for several days now, a couple days now.
This is not new. Okay, this is a real life application of what we have been.
So stop the
talking
video, answer those questions, write down everything that you can get on it.
Okay. Are we ready? Have you
Let's
guys
go.
ready?
We're
Okay.
back.
Okay, so and we're back. We're back live. Okay, so step 4, turn the handle on the electron pump clockwise, so same as before. When the voltmeter reads around 8 volts, disconnect one of the electron pump leads. what does the voltmeter do? Okay.
Okay, so you pump, and when you get to 8 volts, let me know, and I will
Okay.
disconnect this.
All right, and you got both of these in the video. We're good.
Yeah.
Okay, and 5, 6, 7, pull.
Okay, we disconnected it.
That's really good. Look at that. It's right on the money there. Okay. All right. Okay, so what does the voltmeter do?
Looks like
Cool.
looks like it's just sitting there.
It's just hanging out. Okay. And we unplugged that silver
So
lead right there.
there's no path
Ah,
back to the electron pump.
okay. Okay, step 5, bite the connected electron pump lead back on the clip that you disconnected from. Describe what happens here.
Okay. You know what? I'm gonna let you
Here, I can
bite
do
it
this.
back on.
Yeah.
Oops, sorry about this.
You good? You good?
Go.
Okay. Oh, this is okay. Oh my gosh, I'm barely touching it. There we go. Oh,
Doink.
crash and burn. Okay. Okay, so what happened there? It was you guys didn't see when I was connecting it, but I was like barely touching it, like right here, like I hadn't even clipped it on yet, and it was like, you know, it started turning on.
It started turning. So there's some responses here for you to handle, and that'll be the rest of the lesson.
Yeah. So describe what happened here with this situation once I put it back on the clip there,
Yeah.
the lead, and then tell me what. I'm like,
Yeah.
okay, what is inside the capacitor?
We've been talking about it. You should know.
Yeah, just describe, what is inside a capacitor. Describe the journey of the electrons while you are turning the pump handle.
Yeah.
Okay, where are they going? What's happening?
Yeah. Uh-huh.
Okay. Why did the pump handle turn by itself in step 5?
Yeah.
When we clipped that back on there. And then describe how work and potential energy are illustrated in this activity.
Sweet. Something for you to do.
This is good stuff.
It is.
All right.